What is a ring modulator and what is with these wacky waveforms? I'm Professor Fiore and I'm going to explain it to you. Greetings, folks. Today's topic, a passive ring modulator. Now, classically, ring modulators were used for creating in telecommunications a double-sideband suppressed carrier AM radio signal. Boy, that's a mouthful. But besides that, we're not going to look at that application. We are, in fact, going to look at a technique to create interesting new sounds from your musical instrument. You can use a ring modulator to turn pretty much any musical instrument into something that sounds kind of inharmonic, something that has sort of a metallic quality to it. In extreme cases, it will completely alter the characteristic of your instrument. So let's take a closer look. Mathematically speaking, a ring modulator is a 4-quadrant multiplier. Now, this is not just an amplifier, right? You hear the word multiplier. A 4-quadrant multiplier takes into account whether the signal is positive or negative. So it's not like a VCA. A VCA you could think of as a 2-quadrant multiplier. In other words, it takes this input signal, which is positive or negative, and it just multiplies it by a constant value, right? Just makes it bigger. But a 4-quadrant multiplier, the multiplier itself can have a sign, right? So in other words, we can have an AC signal be the multiplier, and if it's negative, then we get an inversion of this signal along with the increase in amplitude. So this is, to make it even more interesting, entirely different from just adding two signals, right? If you have signal A and signal B and you add them together like a summing amplifier, you end up with signal A plus signal B. In this case, we have signal A times signal B. And there's a big, big difference between those two things, right? So as I mentioned, this can be used to create what's called DSB-SC, or double-sideband suppressed carrier. This is a power-efficient way of creating AM signals. But in our case, we are going to look at this alternate way of sort of altering your timbre of your musical instrument, all right? Overtone rich, as I like to call it. Now, the two signals that you're going to enter here, one is your normal input signal from your musical instrument, right? We would normally call that an intelligence or a modulation signal. And then the other one is called a carrier, right? And this is a holdover from the telecommunications, radio kind of stuff. We have a carrier and a modulator, right? Carrier is fixed, modulator changes, right? That's your intelligence signal. Now, here's the interesting bit. When we look at the math of this, the output of your ring modulator does not contain either of the input signals. They're gone. What it does contain are what are called sidebands, upper and lower sidebands. These are the sum and difference frequencies of the two inputs. So for example, if you threw in 1 kilohertz as a carrier and 200 hertz as your modulation signal, your instrument signal, then what you get out is not 1 kilohertz and 200 hertz. What you get out is 1 kilohertz minus 200 hertz. In other words, a sine wave at 800 hertz. And then another one that's the addition. In other words, 1 kilohertz plus 200 or 1200 hertz. So you put in 200 hertz and 1 kilohertz, and what you get out is 800 hertz and 1200 hertz. Now, if you think about that for a sec, that tells you something very, very interesting, because those two new frequencies are not necessarily harmonically related to either of the input signals. Now, when you have these inharmonic overtones, typically people will describe the result as having a metallic sort of sound, the sound of struck metal, right? It's not definitive pitch because the harmonics don't line up as integer multiples. You get these weird sorts of qualities, okay? So if you really crank it up, you get really intense ring modulation because, again, you can control this just like you would with a distortion box, subtle, middle, extreme. If you have extreme ring mod effects, then the sound is completely altered, right? It's not even sort of vaguely familiar with what you started with. Now, ultimately, to follow the math on this, there is one useful trig identity, okay? Basically, what this says is sine alpha and sine beta are your two inputs. And I'm just going to call sine alpha your carrier, and sine beta is going to be the modulation signal. So I'm just looking at two sine waves, the simplest possible case. You multiply these together, and what you get is this quantity. 1/2 is just a scaling factor. I'm more interested in what's going on here. Here you have cosine alpha minus beta, right? So this is what I was referring to as the lower sideband, like 1K minus 200 hertz gets you the 800 hertz. The fact that it's cosine just indicates there's a 90-degree phase shift compared to a sine wave. No big deal. And then here's the other piece, the other sideband, cosine of alpha plus beta. That would have been our 1200 hertz in the example. And it is also a cosine, but it's negative. So it's shifted 90 degrees because it's cosine, but negative means it's inverted. All right? Now, in reality, sine beta is a series of frequencies. Right? You pluck your guitar, or you blow a note into your saxophone, or whatever the heck it is. It doesn't contain just one pure sine wave. It contains the fundamental pitch plus a whole bunch of harmonics. So for each harmonic that you have also interacts with the carrier. In other words, every component sine wave, every component harmonic that you have in your modulator signal produces a pair of sidebands, an upper and a lower sideband that are centered around the carrier. Now, you could also alter the carrier frequency, which sort of translates these sidebands up and down the spectrum, and that creates yet another quality difference, another timbre difference in your output. So typically, if you have a ring mod stomp box, you're going to have some amplitude controls to control just how much of an effect you get, along with a frequency for the carrier, because that will translate everything up and down in the spectrum. All right. So let's just take a look at a simple circuit. Now, there's multiple ways of doing this. A simple passive ring modulator is just a couple of transformers and a handful of diodes. That's all it is. It's very simple. Of course, it's not ideal. There's better ways of doing this. We can actually buy integrated circuits called 4-quadrant multipliers, and they will be more accurate. But, sometimes we do things that might be less than ideal just because we like the, let's call them timbral alternations of the signal. In other words, if you're going to make a fuzz box, you don't really care if you have a super high quality audio quality, super low distortion op amp, right? Because you're creating distortion anyway. So you might actually like some of the not so ideal characteristics in this little passive thing, right? So basically what we do is we feed the modulator signal in over here, and we have the carrier coming in over here, and then we have this ring of diodes. Now at first glance, this looks like a full wave bridge rectifier, but if you take a second look at it, you realize it's not. Because the directions of a full wave bridge rectifier, the diodes essentially would be alternating in direction. Here they're all sort of pointing in the same direction. And that makes a huge difference, right? And then we run this thing out through another transformer, and this is our load that I just stuck a 10K resistor out here, all right? We're just going to run with that. Now, practically speaking, you do have the issue with these diodes having a turn on, about 0.7 of a volt. So what you might do, what I didn't do here, I just wanted to keep things simple. What you might do is use a fairly high turns ratio on here. Like this is just 2 to 1. That's what this 2 over here is for mine. And that's just to compensate for the split on the secondary here. But, if you had like 20 to 1, what you're really saying is the input signal is going to be amped up by a factor of 10. So maybe you've got a few hundred millivolts out here, maybe, close to a volt, whatever the heck it is. Coming out of here, you're going to have several volts, maybe 10 volts, right? And then, of course, we'll scale it back down on the output with that same sort of transformer. These aren't different transformers, right? If this is a 20 to 1 transformer, this is a 20 to 1 transformer, because here you're putting the signal on the primary, you're taking it off the secondary tapped. Here, the input to the transformer is the secondary tap, and you're taking it off the primary. So this would scale it up, and then this would scale it back down. All right. So to keep things simple, I just said, well, I'll use the 2-to-1, and then I'll just put in big signals over here. So I have 10-volt signals. All right. These are 10-volt peak signals for the modulator and the carrier. And these are just sine waves. All right. That's all they are. So what I'm going to do is I'm going to come in here. This one is set at 1 kilohertz, which is the example I used initially. And this is set at 200 hertz. So we should create 2 sidebands at 1200 and at 800. All right, at the 1K and the 200 should be gone. So let's just take a quick look at this. I'm going to use a transient analysis. Let's see, is that 10? That will work fine. 10 milliseconds. Okay, so here's our output. Now let's go change some of these colors because this is looking a little wacky here. Let's make that blue. That stands out much better. Here's my input sine wave. Let's see, what do we want to make that? Let's make it teal? I don't know. Oh, that's too close. No, let's not do that. Okay, how about, it doesn't really look an awful lot like teal to me, but what are you going to do? All right, let's go to maroon. What the heck? All right, that's dark enough. Okay, so which is which? All right, so the carrier, which is the high frequency sine wave, is the green. That's 10 volts peak. The sort of maroon, that's the modulator. That's the 200 hertz sine wave coming in. And then the output of our ring mod is this funky looking blue thing. Like, what the heck is this? Well, to get a better view, let's separate those curves. Here's our V out, right? So this is like, what the heck is going on here? The first thing I want to point out is what looks like some kind of a symmetry here. Like this thing kind of comes up at this little angle, drops down, comes up, drops down, comes up. And then this sort of is a mirror image of it, right? You could imagine like right here, it's being folded, right? This folds on top of here. That's essentially due to the phase shift we were talking about, right? As a 4-quadrant multiplier, right? This signal is negative. So compared to this thing, it's flipped, right? So we're seeing this sort of flipping. It's repeating. When you look, this is actually the convenient point to look right here on this dotted line. Positive, negative. This is coming up positive initially, but over here it's flipped negative. So this negative combined with a negative and a negative gives you a what? Gives you a positive. So I got a positive slope here and a positive slope here, and it just keeps on going. All right. Woo, okay. But, when we look sort of like in the middle, you can see how this thing is tracking, right? This is going negative and then positive. This is going negative and positive. That's, looking good. Over here, looking at this part, see this part's going negative, but this part's going positive because this is the 4-quadrant thing that I'm talking about, right? All right. Well, there's really at this point 2 questions. Like, how do I know that this funky looking blue waveform actually consists of an 800 hertz sine and a 1200 hertz sine? I mean, looking at this, you might not think that. And I will say that it is not perfect. There is a little bit of other garbage in there, as I mentioned, but those are the major sort of contributors to the signal. How do I know that, right? How do I figure out the constituent elements? Secondly, how is this thing actually working? You know what I mean? Like compared to, you might have looked at this and said, I expect to see something that kind of looks like a rectifier. This looks sort of like a full wave rectifier. This isn't rectified. What the heck is going on? How is this actually working? Okay, well, let's take a look at the first question first, which is how do we determine the frequency components? Well, an easy thing to do there is just do a Fourier analysis. So I'm going to set this up. Let's see, we got 200. So let's do a base frequency of 100. And what'll end up happening is we're going to get 16 harmonics. So this is going to go 100, 200, 300, 400, all the way up to 1600 hertz. and it's going to tell me the amplitude and the phase of each component at those frequencies. Now, there might be things in between. In other words, there might be something at like 592 hertz that we're not going to see here. But theoretically, we really should only see the two things, right? Like I said, maybe a little bit of garbage too. Let's go find out. Okay, stretch this open. Now, those of you looking on a small screen probably can't see all these. What I will say first of all is all of these components, for the most part, are measured in milli or microvolts. They're small potentials, okay? And K over here is just the multiplier of the base frequency, right? So 1 times 100, this is 100 hertz, 200 hertz, 300 hertz, 400 hertz, so on and so on and so on. And as we go down, we can see, okay, there's the DC offsets, 122 millivolts. We got 117, 118 microvolts at 100 hertz. We got 105 microvolts at 200 hertz. Hey, we had a nice big signal at 200 hertz, right? There's nothing at 300, 400. Well, we're getting like 500 millivolts, so there's a bit of garbage in there, but not that big. We don't get into something big until we get to 8 times. In other words, 800 hertz, which is what we're expecting. And that's 4.3 volts. This is 4 1/3 volts, right, compared to micro and milli. So this is a big contributor. Phase angle here is 0, and the reason why it's 0, virtually 0, is because I'm using this form of output. I'm using a cosine output, and that's what we expected looking back at that trig identity, okay, cosine output. Anyway, this continues along. 900 hertz, virtually nothing. The kilohertz, 150 microvolts, again, nothing. 1100, same thing. And then I get to 1200, which is the upper sideband. Once again, there's about 4 1/3 volts. The other biggie. And this one's 180, right, for a cosine, which is exactly what we expected. Then as we continue on, again, microvolts, microvolts. Got another one here in a few hundred millivolts. But again, this pretty much shows, this verifies that the two big components you're getting out of here are these upper and sidebands, these sum and difference frequencies. Okay? Beautiful. Fortunately, I can't play this back. I don't have a way of antenna of sort of playing back this signal. But if you build something like this, plug in your guitar, whatever the heck it is, your keyboard, and you're going to get some weird kind of tones. So the next question, the second question is, well, how does it actually work? What's going on here? Well, if you think about this, again, getting back to a rectifier, you would only have one input. Just ignore V carrier for a sec, right? So, what ends up happening, D2 and D4 you'd have to flip mentally, but, you get a direction of current. Basically, as the input signal goes positive, it turns on like D1, right? It goes through a load, it goes through the other diode, the D, where D3 would be, and we get that positive half wave. And then when we go to the negative half wave on the input, the other set of diodes start conducting, and it just flips direction. It's fairly straightforward as far as figuring out how it works. The tricky bit here is that when we have an input signal coming in, right, so it goes positive, does that, as it goes positive, right, I'm sitting over here on D1, does that make D1 forward biased? Well, maybe. Why do I say maybe? Because that also depends on the carrier, right? The carrier is being fed over here. So depending on the amplitude of the carrier, this signal could actually be negative. Even though the input's positive, this signal could be negative with respect to this voltage over here, meaning D1 would be off, not on. Even though this is a positive input, because of V carrier, this thing can be turned off. And the ones that were off can now be turned on. Interesting. Can I come up with a way of maybe showing you this a little better? And the answer is yes. Let's take the carrier and turn this from a sine wave into a square wave. All right, I have to turn this back into a 10-volt peak and turn this back to 1 kilohertz. Technically, what we have now is something called a chopper, but you'll see what the difference is when we do the transient analysis. Ooh, notice how these things line up. I'm going to separate these out again. Look at this, right? Now, we had a sine wave carrier before. So we saw this like sine times sine with this weird kind of lumpy looking thing, right? It's weird because that's sine times sine. So it's not a sine in and of itself, right? Sine times sine. This, however, it's kind of like saying on off, right? Because it's just a square wave. High, low, high, low, high, low. What's happening over here? You're going to multiply this wave by +1 or -1. That's the way to think of it. Okay? All right, so this is +1. There's the input waveform. This is -1. There it is, but flipped upside down. Okay? Same thing over here, right? So this goes plus, this is plus, boom, plus. Right? This is minus, this is plus, so this is minus. And you can see what's happening here, right? So this piece is this piece, but then when this changes from high to low, right, this was going negative, so now it's negative, negative, which makes this positive. All right? Kind of cool. So here in the middle, we had a positive pulse because this was positive, positive, positive. Over here, this is negative, but this is now negative, so it comes back positive again. You start monkeying with the frequencies you're using. If I change the mod to 900 hertz or 750 hertz or something like that, these waveforms are going to change radically. But I think this kind of points out exactly what's happening. So here's your positive modulation signal. All right, well, I have an even larger carrier over here, plus plus. Okay. But a moment later, the carrier goes negative. So what is this? All right. It could be enough. It could be negative to turn D1 off, right? It's a much more complicated situation because you've got two waveforms going on at the same time. Well, that's all well and good, right? But the bottom line is, if you plug your guitar into this, you plug your electric keyboard into this, you get some fun new sounds. Hey, play with the values, increase the carrier, decrease the carrier, change the carrier frequency, whatever you want to do. Listen, you like it, that's fantastic, right? Great. Okay, hope you enjoyed this. I'll see you next time. Take care.